Every year, the world produces more than 800 million tons of glass. Remarkably, nearly all of that enormous volume begins as sand, one of the most common and seemingly ordinary materials on Earth. Glass may appear fragile, yet this is the very material that has quietly supported human civilization for centuries. Its journey begins in silica mines, where only a small fraction of sand deposits are pure enough to meet the demanding standards of the glass industry. From there, the material travels through massive industrial processing lines and into furnaces hotter than molten lava, where it is transformed into a glowing lake of molten glass. From that single material, humanity creates the transparent windows that shape our cities and the glass bottles found in virtually every corner of modern life. So how did ordinary grains of sand become one of the most important materials in human history? Join Factron Process as we uncover the entire process. At its core, glass is a rather unusual material. While the atoms inside metals or gemstones are arranged in highly ordered patterns, the atoms in glass become locked in a disordered state as the material cools. This unique structure gives glass its characteristic transparency, while also making it both hard and brittle. Yet, when engineered correctly, glass can become surprisingly strong. Humans have been making glass for more than 4,000 years. In its earliest forms, it was mainly used for jewelry and decorative objects. Over time, however, it evolved into one of the foundations of modern industry. A famous example is the Prince Rupert's drop, a glass droplet whose bulbous head can withstand tremendous impact, yet shatters explosively if its thin tail is broken. Today, China produces more than 50% of the world's flat glass, while glass is used in over 90% of modern buildings, in one form or another. From bottles and windows to skyscrapers, glass has become a material that helps humanity preserve, observe, and build. It may appear fragile, but it quietly supports the modern world every single day. Everything begins with the extraction of one of the most common materials on Earth, sand. Although it appears almost everywhere, only a small fraction of sand is suitable for making glass. This is high-purity silica sand, sometimes reaching up to 99% purity. Often found in ancient quartz deposits, riverbeds naturally filtered over millions of years, or silica-rich sandstone layers, such as those in the state of Wisconsin in the United States. To reach this special raw material, mining teams drill holes dozens of feet deep into the rock and load them with industrial explosives. In just a few seconds, a single blast can release more than 20,000 tons of material. As the dust begins to settle, massive excavators quickly move into the site, collecting the ore and loading it onto heavy-duty dump trucks. At first glance, it may not look remarkable, but the silicon dioxide hidden inside these rocks will become the foundation for everything from glass bottles and windows to skyscrapers wrapped in glass, hundreds of feet tall. If ordinary sand containing too much clay, iron oxide, and other minerals were used instead, the glass would turn cloudy, develop bubbles, and lose the transparency that gives this material its greatest value. When silica arrives at the plant, it must go through a strict refining process. First, the material is crushed and sent into high-capacity washing systems, where hundreds of tons of water continuously wash away impurities, clinging to the surface of the sand grains. Next, gravity separators, magnetic separators, and classification screens remove unwanted minerals, especially iron, the greatest enemy of transparent glass. Even a small amount of this impurity left behind can tint the final product, or reduce the clarity that defines the value of glass. In some modern plants, the entire system can process up to 220 tons of sand per hour. After multiple rounds of washing and separation, what remains is almost pure silica. Only when it reaches the required level of purity is it allowed to enter the furnace. After being refined, silica still cannot become glass on its own. First, it must enter a stage that may seem simple, but determines almost the entire quality of the final product: batching. Here, silica is mixed with soda ash, limestone, and other additives such as dolomite or alumina, according to tightly controlled formulas. Soda ash helps lower the melting point of silica from more than 3,100 degrees Fahrenheit to a level more suitable for industrial production, while limestone helps make the glass more resistant to water and chemical attack. Dolomite adds magnesium to improve stability, while alumina helps increase hardness and resistance to cracking. Hundreds of tons of raw materials are then weighed by automated systems, with errors measured in tiny fractions of a percent before being sent into high-capacity mixers. In the glass industry, even a small mistake in the batch ratio can affect the color, strength, and overall quality of an entire production run. After being blended, the raw material mixture is fed into the glass furnace, the hottest and most critical part of the entire plant. Inside the furnace, temperatures are typically maintained between 2,730 degrees Fahrenheit and 3,000 degrees Fahrenheit, hot enough to transform silica sand, soda ash, limestone, and other additives into a thick stream of molten glass. This is far more than a simple melting process. At these extreme temperatures, the crystalline structure of silica breaks down, the ingredients begin to fuse together, and an entirely new material network starts to form. Glass furnaces usually operate continuously, 24 hours a day, 7 days a week, because cooling down or restarting a furnace can take several days. From the outside, everything appears to be controlled by sensors and computerized systems. Inside, however, lies a glowing lake of liquid material hotter than molten lava. After many hours in the furnace, the original powdered mixture disappears completely, replaced by molten glass with the temperature, viscosity, and chemical composition required for the shaping processes that follow. After many hours inside the furnace, the raw material mixture has melted completely. However, the molten glass still contains millions of tiny bubbles formed during the melting process, along with regions where the temperature and chemical composition are not yet fully uniform. That is why the glass must remain in the furnace for an additional 24 to 48 hours to undergo refining and homogenization. During this time, the burners continuously supply heat, creating natural convection currents throughout the molten glass bath. Tiny bubbles gradually rise to the surface and disappear, while temperature and chemical composition become more evenly distributed throughout the material. If these imperfections were left behind, they could become weak points that reduce strength or create distortions, hazy spots, and visual defects in the final product. From the same molten glass bath, the industry can create completely different products. Depending on the final application, this glowing stream of material is directed into separate forming lines. One branch moves into the float glass process to create flat sheets used in windows, building facades, and electronic displays. The other branch is cut into precisely measured gobs of molten glass to produce bottles, jars, and other glass packaging. The same material begins two entirely different journeys, each using a forming technology optimized for its own purpose. For flat glass, the greatest breakthrough in the industry was not melting the glass, but finding a way to create a perfectly flat surface. Float glass technology, introduced in 1959 and now used for nearly 90% of the world's flat glass production, completely transformed how glass is made. Instead of being pressed or rolled like many other materials, molten glass is guided from the furnace onto a bath of molten tin, hundreds of feet long. A fascinating physical principle takes over. Because glass is lighter than tin, it floats on the surface of the liquid metal instead of sinking. Under the force of gravity and surface tension, the molten glass naturally spreads into a flat layer, with two nearly flawless, glossy surfaces, without the need for mechanical polishing. Meanwhile, rollers on both sides continuously adjust the pulling speed to control the thickness of the glass, from about 0.08 inch for thin glass to more than 0.9 inch for specialized applications. By the time it leaves the tin bath, the glowing material is no longer just molten glass. It has become a continuous glass ribbon up to 10 feet wide, ready for the next stages of processing. The glass sheet cannot be cooled too quickly after leaving the forming section, as temperature differences can create internal stresses that make the glass more prone to cracking. To prevent this, it passes through an annealing layer, a cooling chamber that can stretch up to 600 feet in length, where the temperature is gradually reduced to stabilize the glass structure. Heat is carefully controlled in different zones so that both the surface and the core contract evenly. Once stabilized, the glass moves through an automated inspection system. High-resolution cameras scan the surface for bubbles, scratches, and foreign particles, while laser sensors measure flatness and thickness. Any sheet that fails to meet quality requirements is rejected or trimmed to remove defective areas, ensuring that only clear, flat, and structurally stable glass proceeds to commercial use. The glass sheet is then processed further to meet different construction requirements. Automated grinding systems smooth and strengthen the edges, making the glass safer to handle and install. For applications that require greater strength, the glass is heated to approximately 1,150 degrees Fahrenheit in a tempering furnace, and then rapidly cooled with high-pressure air, increasing its impact resistance several times compared to ordinary glass. Some products also receive a low E coating, an ultra-thin metallic layer that reflects heat while still allowing light to pass through, helping improve energy efficiency in modern buildings. For projects that demand better thermal and acoustic performance, 2 or more glass panes are assembled into insulated glass units, with a layer of dry air or argon gas sealed between them. These advanced processing technologies transform a simple sheet of glass into a high-performance material capable of reducing heat transfer, lowering noise levels, and serving in modern structures hundreds of feet tall around the world. Leaving the flat glass production line, we now explore how factories create thousands of identical glass bottles every hour, and it all begins with small drops of molten glass, controlled with remarkable precision. After leaving the furnace, the molten glass is guided into a feeder system, where its temperature and flow rate are continuously controlled. The glass then passes through precisely designed openings before being cut by high-speed shears. The result is a series of molten glass drops called gobs, each produced with nearly identical weight. For a typical beverage bottle, each gob usually weighs around 0.6 to 0.8 pound. Molten glass drops are released into a preliminary mold, called a blank mold, to create an intermediate shape known as a parison. You can think of the parison as a miniature version of the final bottle, with the neck already formed, while the body remains thick and short. At this stage, compressed air, or a mechanical plunger, forces the molten glass to distribute evenly inside the mold. This step is especially important because it determines how the material will be distributed throughout the entire bottle later on. Leaving the blank mold, the parison is quickly rotated 180 degrees by a mechanical arm and transferred into the final mold. Here, a stream of high-pressure compressed air is blown into the parison, forcing the molten glass to expand in every direction until it presses tightly against the mold walls. This is the moment when the bottle is truly born. In just a few seconds, what was once a simple intermediate shape now takes on all of its final features. From the bottle body and shoulder to the distinctive curves that define a particular brand. Remarkably, all of these details are created using nothing more than air pressure and carefully controlled molding. On modern production lines, the entire process, from the moment a gob enters the mold to the completion of the bottle's final shape, typically takes only 10 to 15 seconds. During that time, the glass must be distributed evenly throughout the bottle wall. If one area is too thin, the bottle may break during transportation. If it is too thick, manufacturers can waste millions of pounds of raw material each year. That is why modern forming systems continuously monitor air pressure, temperature, and blowing time to ensure that every bottle leaving the mold is nearly identical to the next. Freshly removed from the forming mold, the bottles are still at temperatures of several hundred degrees Fahrenheit and contain an invisible problem: internal thermal stress. During the forming process, some areas cool faster than others, causing uneven stress distribution within the glass. If left untreated, the bottle could crack or shatter during transportation or use. To eliminate this issue, the bottles are sent through an annealing layer. The temperature is gradually reduced in a carefully controlled manner over a period ranging from about 30 minutes to more than 2 hours, depending on the size of the product. This process allows the internal glass structure to stabilize and relieves any remaining stress. Once cooled, each bottle moves on to an automated inspection line. High-speed cameras, laser sensors, and machine vision systems examine wall thickness, bottleneck dimensions, bubbles, cracks, and other defects that may be difficult to detect with the naked eye. In modern facilities, hundreds of bottles can be inspected every minute. Only the products that pass all of these quality checks are cleared to leave the production line. At first glance, glass seems like a fragile material. Yet the remarkable truth is that this seemingly delicate substance helps support a significant part of human civilization. Its story begins with tiny grains of sand, so ordinary that most of us never give them a second thought. But through science, engineering, and centuries of innovation, humanity has transformed those humble particles into bottles that preserve food and medicine, windows that fill our buildings with light, and the glass surfaces that connect billions of people across the world. And how many other everyday materials are hiding stories just as extraordinary? If you enjoy exploring the industrial processes that quietly shape the modern world, subscribe to Factron Process and join us on the next journey.